recording. Yeah. So my basic question is, what we are trying to do with parallelism is execute subtasks simultaneously and get the job done. My question is, can every task that we get chunked into smaller tasks and get the result back? Is it possible? Yes. What is your thought on that? Have you ever wondered, okay, whatever the task that we have can be parallelized, or is it not? Yes, what is your thought on that? The answer is not every problem can be break down to smaller tasks. Yes. Yes, the answer is correct. No, because some subtasks cannot be independent on each. Yes. If we have a task that is depending on another subtask, okay, we have a set of subtasks. We are trying to execute those subtasks simultaneously. But the problem is, if one of those subtasks is depending on another task, then what will happen? You can't execute parallelism because one task is depending on another. So we have to complete that task first, then we need to execute the second one. So if there is any dependency between subtasks that we are trying to execute, if there is any dependency problem that we are having, then parallelism cannot be achieved using that. Okay, so remember, yes, most of the tasks that we see can be sequentially executed, but not all. Okay, so there is a situation where parallelism will not work. Okay, that is keep that what do you call, keep that in your mind for sure, because don't think everything can be parallelized. If that is the case, we are in a really, really happy world. Okay, my next question. The next question is that I'm going to ask is, should, if say for some reason, we can break down, there are no dependency issues, that everything, the smaller subtasks that we do executing have no dependencies, they can execute simultaneously, no problem at all. The subtasks are independent of each other. They are good for parallelization. They can be executed parallelly. And do you think that if we take a task and execute that task in serial manner and get the result, and the same task we execute it in parallelly and get the result back? So we have this task, we have a task, we take the task, execute serially, no issues. And we take the same task, make it parallel, execute, get the results back. Okay. So we have the result at the end. Would you think that every time the parallel task will be executed in less time? Okay, so we achieve parallelism to achieve some task or get some task done very quickly, right? That is all about parallelism. Okay, we execute some task, we get the result as much as possible, as soon as possible. So we execute the task in serial manner as well as the parallel manner. My question is whether we're gonna get the parallel result much quicker than the serial one, as all the time. Will it be true? I hope you guys get the question. We have the problem, we execute in serial, we execute in parallel, we get the result, And my question is, will the result that is produced by serial and parallelism is gonna beat the time it takes to complete the task? Always the parallelism will win. That means the parallelized task will be completed very quickly. Is that gonna be a thing? You hope you guys get the question. We have two. Um, uh, will parallelism always win over? Yes. What are your thoughts? What do you think on that? Yes, let me know. Yes, I think the parallel manner will complete in less amount of time. Okay, that's fine. What about others? Others, what do you think? I'll be using my pen. Yes. Okay, pen works. That's fine. So we have the serial task and we have the parallel. So we execute the serial one as the parallel one. So my question is, will parallel always win? Which will take less time? Which one will take less time? In simple tasks, serial compute can be speed. Yes, that's the question. That's the correct answer. So not all the time when we are thinking about uh, parallelization, when we are executing any task, don't get the notion of that always doing thing in parallel is the best solution. No, that is not the case. There are some scenarios where serial is more efficient than the parallel. Anyone knows why? Why, if we are dividing the work and a lot of subtasks are executed under here, basically it should win, right? Rather than, let's assume this is a one single machine, okay, one single core machine or something like that. If rather than a task is carried out by one single core, if we can have multiple cores, let's say in here we have 4 cores in here, rather than some task carrying out by one single core, 4 cores should be always faster. Yeah. Why it is not happening? Why it is always not winning? Why it is not always the less time? Any guesses? Or anyone have the answer? That would be great. Why it is not happening? Say, for example, if you take something that I encountered recently. So I'm taking this in a physical world, not in computer, nothing to do with at all. So I have 1,000 bricks to transfer from one place A to place B. Okay, I have 1,000 bricks. If one person do that, what will happen? He have to carry out 1,000 bricks. Okay, if that the same person or like the same strength or same PCA logic, if he use 4%, then each one of these will carry out these simultaneously. So one have to carry out 250 since there are no dependency on each other. The time should be around 1/4 of that. Okay, one person is taking 1 hour, then all the 4% should take only like 15 minutes. Correct? Right? So why it is not applied in serial and parallel computing in general? Why it is not happening? Any suggestions, any guests? Why this model is not working? Yes. Any simple guess? I don't mind the right answer. Okay, I'm not expecting the right answer. I'm just asking why that's not happening. Should always win, right? If you think in a way, any simple solution, any simple thing that might be affecting this. Anyone, anything. Oh yes, parallel computing requires additional time for coordination and managing multiple processes. Exactly. The same reason. So if you carried out something in serial, what will happen is the serial task has nothing else to do. It start executing all the task and it get the job done. But in parallel computing, that is not the case. In parallel computing, what we need to do is we need to divide the task. Okay, and we need to check whether those tasks are depending on each other. Okay, and once those once the task division is done, okay, and each of core assignment and task is breakdown and everything is in motion, and then we need to execute those tasks. Okay, after every execution is done, we need to gather the result on each of these execution and make the final result, and we need to present. Okay, by this time, sometimes the serial computation that we are doing, it may be done already because there is no additional time, additional coordination, additional time division on task. Nothing is happening. The thing that the task that we assign is already executed by the serial task is completed. So we don't have to think that always parallelism is going to be okay. But if you take the example, the real world physical example, say for example, uh, rather than moving 1,000 bricks, okay, I talked about sorry, um, this is not drawing. So we have 1,000 bricks to move, okay, by one single person, okay. And if I use one single person to do thing, he have to move 1,000 bricks. But if you use 4 people, then what will happen? Each one will only uh, go with uh, 250, as we assume that everyone is working at same pace and same level. They have same physiology. But in a case where we have only 10 bricks, okay, we have only 10 bricks, and we have one person, okay, the one person would be transferring 10 bricks, then that would be done. But if you have 4 person, what will happen? Each one will be dividing 2.5. That's fairly an assumption, like we have half a brick or something like that. Okay, so you guys see the number of items that we have is a major factor when we are considering parallelism. Okay, so you guys see the problem in here as well. Something around we did not expect 2.5. The data representation, how we going to divide 2.5 among four of the people. Okay, is somebody going to carry half a brick, or somebody is gonna or 2 person is gonna carry one brick, or 2 persons gonna carry one brick. So there are decision making to be done in here. Okay, there are decision making done to be here. So who's gonna take first two? Okay, who is gonna divide these things? So the initial cost, the initial preparation that we do in parallel computing can be cost. Okay, there is an initial cost, there is an initial requirement, initial decision need to be done in order to make it parallel. Okay, but in single person job, we have no dependencies. In this scenario, all you have to do is move 10 bricks from place A to place B. Okay, so there is no dependencies, there is no additional task, additional things. How we going to manage these things? There is no requirement at all. So by the same logic, the amount of data, the amount of processing data that we need to do play a key role in what we are trying to achieve. Okay, if there is less amount of data that need to be handled, then serial might win. I'm not saying serial is always winning. That means serial execution will be much faster. Not saying that. Okay, based on the number of data, usually based on the number of data is less, then the serial computing might be more efficient. Okay, in parallel computing, if the amount of data that we are trying to process, in here we have 10. Okay, if we have less amount of data and we are trying to use parallel algorithms or anything like that, if there is less amount of data and a lot of parallel addition to be done, then the parallel solution might not work. Okay, this would not work. Okay, remember that. So amount of data that we are processing is a key major uh, role in whether we are getting the less amount of time for execution. Okay, not always serialization mean, not always parallelization mean. If there is less amount of data, serialization might win. Okay, if there is lot of data, then even a serial task might be executed in parallel way, that might win. Okay, so remember the number of data that we are having, number of data is what we are having, play a key role in serialization execution and parallel execution. Okay, so that's thing. I hope you guys understood that. Yes, anyone have any questions we can discuss right now? Raise your hand if you have any questions. Why data points matter? If you have any question, just let me know. Okay, that's perfect. Another reason that we need to think about when we are executing things in parallel, the data, we talk about data amount, right? 100 amount, 100 data points or 10 data points, depending on the data points that we need to consider the choosing parallelism over it. We will see this in action, like we will execute some algorithms. We'll make it parallel. We will have less amount of data and see the result. We will add millions of data and see the outcome. Okay. So one thing that we need to remember, number of data points matter. The second thing that I want to emphasize in here is that um, if we are moving ahead, second, I don't know, it's have the same, not allowing me to change the size of the pen. The second point that I want to emphasize is that the data type. Okay. In most of the programming languages that we have, I'm not sure whether you guys have heard, um, there are uh, types like what we call primitive type. Okay, anybody have heard about primitive types? Raise your hand. If you are coming from languages like Java, you might have heard primitive data types. Anyone heard about primitive data types? Raise your hand, please, if you have heard about it. Yes. So primitive data types include something like integer, bool, and char. Those are considered as primitive data types. These are like what we call primitive data types. So these primitive data types, um, what they hold is uh, the direct access for the memory. Okay, they don't have what we call wrapping, loading, and unloading process. Okay, if you are not familiar with those things, I can explain it a little bit more later on when we are doing the practical. But remember, data types like primitive types, when we are using those things in our algorithms, they are much faster. There are what we call wrapper uh, wrapper data types, or we call these things as non-primitive types. Example, the uh, integer wrapper type we call integer. Okay, Boolean wrapper type we call Boolean. Okay, and character we have something called, if I'm not mistaken, char. Okay, so there are primitive types and wrapper types. Okay, so we need to be very careful what we are using within in our parallel or serial algorithm. Instead of using primitive type, if we use a wrapper type, our serial execution might be faster. Okay, if we use within our application, within our parallel algorithm, if we accidentally use anything like these wrapper classes, what will happen is there are some additional steps that need to load and unload these data types. Okay, so we need to be really careful selecting the data that we're going to be exploring. Always remember, when we are working with parallel computing, make sure to use primitive data types such as Boolean, char, and integer. There are like 7 or 8 in Java in general. If you are trying to work with Java um, parallelization, make sure to use the primitive types. There are other frameworks or other programming languages have the different concepts around it. So make sure the highlight or the point that I am to emphasize in here, the data types matter. Okay, data size matter, how many data are in their data points, and what is the data type. Okay, if you are using the wrong data type, then what will happen? It's not gonna work as expected. Okay. Okay, I think I have the conclusion here. Right. So two things that I have discussed so far. First is amount of data, and the second one is the uh, data type. Okay, so that's drastically affect our parallelization in action. Okay, the next thing that we need to do is we need to understand what are the other factors we will encounter in terms of parallelization. Okay, two factors we talked. The third one is definitely the memory model that we are using. Or we can simply say the amount of RAM or amount of uh, uh, what do you call this, cache memories that we use. That is a primary thing uh, we will be affecting in our parallel executions. Okay, so you guys have heard things like L1 cache, L2 cache, and those kind of things. Okay, if we have more and more speed memory, then we are having good parallel algorithms. Okay, so the more memory that we have, more execution it can perform. And also remember, not only memory, then we have CPU or processing unit, that is also a key point. So altogether, these two things is what we call hardware. Okay, so hardware matters. Okay, we need to choose the correct hardware for doing parallel computing. Okay, so there is a different hardware mechanisms or hardware practice that we take into consideration when we are doing parallel computing. So one is the CPU and memory bounded one, the hardware one. The second one is the most popular one is GPU based one. Anyone knows what GPU has to do with? GPU, anyone knows what GPU stands for? Graphical Processing Unit, GPU. Okay, so GPU came around things like processing graphics. So what it has to do with parallel computing? Why GPU is so important in parallel computing? Anyone have any guesses? So why GPU is important in parallelization? Why you guys know that CPU has the capability of executing things parallel. Right now, what we are using to work within our most of the time when we are working in our machines, we are using our CPU to do the parallel things. Okay, it's uh, showing us some detail. It is calculating time. It is recording my audio. It is uh, doing the kernel stuff, memory management, all those things. It's running Zoom as well as it is running Chrome. And there are a lot of tasks happening in my CPU, which is executing in parallel. Okay, so GPU is doing the task very well. Why do we need GPUs then in order to achieve parallelism? What is the key component that GPU holds to parallelism? Anyone knows why GPU is so important in parallel computing? And if you guys do not know, the world most valued company at this moment, it might change, is a GPU manufacturing company. Okay, so all of a sudden, why GPU is so important in parallelism? It helps to break down the task. It does kind of it. GPUs have huge number of cores. I'm gonna say no. It's not what we think as cores. So CPU, you guys know that in CPU architecture, we have cores, right? If you look at your machine, you will have 8 core, 6 core. That means the CPU is divided into smaller processing units kind of things. But GPU, they don't share the concept of cores. Okay. The ability to handle, so GPU has a different terminology for this. It's not called core, but is something similar if you think. But for your information, I will let you know what we have in GPU is a thread. Okay, it's not the thread that you are familiar with, the CPU threads, and not something like that. We have threads in GPUs. Okay, but it is something similar. Okay, it's not 100%. Okay, it's not 100%, but somewhat equal. I'm not sure whether that color is visible. Somewhat equal. Okay, I'm not saying totally equal to cores and threads. GPU has huge numbers of cores, as I've seen, and the ability to handle large number of simultaneous operation efficiently. Of course, CPU can do that as well. So one answer says uh, ability to handle large number of simultaneous operations efficiently. CPU is also doing that. CPU is handling that very perfectly. GPU is also doing the same thing. Okay, CPU can handle multiple tasks very well. It has been doing for a lot of time. GPU are like recent introduction. So why GPU is so important in this scenario? Why simulations, sorry, parallelizations, GPUs provide a huge role. If everything can be, you know, the CPU is multitasking. CPU can do parallel tasks. Why do we need GPU? So if you go back to the origin of the GPU, you might find a little bit of answer. Anyone knows the history behind the GPU? Why GPU is originally created? CPU, GPU architecture. So why it was created? If anybody knows that, the answer resides that. Why GPUs initially created? What's the purpose of a GPU? Yes. Why GPU? I'm not sure whether you guys can see these things. Uh, I have selected the thickest line, but it's Yes, any guesses? What was the initial usage of uh, a GPU? Why do we create a GPU in the first place? Why GPU? Why do we need GPU? What is the first place? Anyone have played games earlier on? Need for speed or anything similar? If you have played a game, you know most of the games are expecting use GPU. Yes, to accelerate graphic rendering, the GPU was introduced. Okay, so then the problems comes in. Why CPU can't do the accelerated graphic rendering? Why? What's the reason behind GPU's use rather than the CPU to accelerate the graphics? Any guesses? Why CPU is not usable in that scenario only? Anything like playing music, doing doing rendering or something like um, playing a song, making internet connections, doing rendering browser, uh, getting internet connectivity. The CPU is doing well, perfect. Why only GPU, graphic rendering, has to be accelerated using GPUs? Why it was there in the first place? Yes, any guesses, guys? Why do we need GPU in the first place? Yes, any guesses? Anything? You don't. It won't have to be the correct one. CPU has no direct access to the pixel on screen. GPU has them. Well, before GPUs, then how do you think graphics were rendered? I don't know. GPUs was came to party later on. Earlier days, we had only VGA port. I'm not sure whether you guys have seen that era, but I was there when we have like 486 Pentium 1, Pentium 2 era. We had no GPU. We haven't heard about GPUs until we were like uh, Pentium 4, Pentium 4 era. That's that's we heard about something like a GPU. Not even a GPU, it was called AGPU or something like that, accelerated graphic card. Yes. Any other good guesses? But I highly admire your attention, attempting to give an answer. Yes. Any other guesses? Why do the CPU failed on processing graphics? Everything works fine. So the main reason the GPU was invented is to offload its work. Okay. What load? The image generation, the graphic generation can be done using a GPU. Why only graphic generation? Why we can't do sounds and other multitasking processing like that? No. The GPU is designed in a way that GPU is capable of executing Okay, let's say this is the GPU. Okay, I'm just highly accelerating, and I wish I have much more thicker line to draw this thing. I don't know why it is drawing in such small. Yeah, knows how to thicken this line. It's very small. I have a laser or something like that. Yeah, that's good. But it's going away. Let me check. And shape, line, text, sticky note, comment, middle. No. Even the highlight, I have the burst colors. Give me a second. Just give me a second, guys. I'm trying to figure out why it is not sticking enough. Oh, that's strange. Okay, never mind. I'll just use very bold pen. Might use something. Let's do something. So we have a GPU in here. So this is the GPU. Okay. So when a GPU is tasked with something, okay, let's assume that it is given a single task to execute simultaneously. The best thing about GPU is it is executing a task on all of these cores or threads, what we call, in one single go. Okay, so if you guys can remember, I think you guys have seen that model, what we call. Let me give you guys a refresher. We have the what we call this is Finn's classical taxonomy. Okay, in there we have uh, four categories: SSID, single instruction, single data stream, and we have SIMD, single instruction, multiple data stream, and we have MISD, multiple instruction, single data stream, and we have MIMD. Okay, that means multiple instruction, multiple data stream. Okay, so out of those things, we will be working with in this scenario in GPU section. So in GPU section, what we do is it's gonna be a single instruction and multiple data. So single instruction, multiple data, it is this one in here. So GPU is coming under GPU is coming under single instruction, multiple data. Okay, so we need to make sure um, we are giving one single instruction in here and the multiple data sources are provided. So how that helps us in terms of uh, GPU and accelerated programming. So as long as the instruction is to do one single task and we can provide multiple data on it, then the GPU can execute really good uh, output for one single type of instruction. Let's say calculate the 1 plus 1 or addition. Okay. So all of these threads in the GPU will have add function. All of these threads. Okay. So the data that we are providing is going to be different. The function is going to be add. Okay. The function is going to be add. And the data that we are providing is going to be different. So how that is helping with our computational task. Why CPU is not working and what it's not working for parallelization in this scenario. So the basic reason is that single instruction, multiple data. So we can only give one instruction, as we mentioned, add. The data can be X and Y. Okay. The second core is also providing X. The second thread is going to be doing the same instruction. Let's say add. Data will be A and B. Okay. So we have the single instruction. Instruction is add, but multiple data. Okay. So GPU is coming under this category. And this kind of operations is something what we call operation that need to be happening almost every time. Okay, let's take the example of our graphical unit. Okay, what is our graphical unit? Let's take the example of our display. Okay, so in our display, let's assume that this is a highly accelerated one. We have 4 pixels to render. Okay, but nowadays in standards we have like millions of pixels for demonstration or explanation purpose. Let's assume that we need to show 4 pixel display. Our display is 4 pixels. So in this 4 pixels, we need to calculate the RGB value. Okay, if this is red, if this is blue, and if this is red, and this might be green. Okay, so based on these RGB values, we will get a pixel value. Okay, what we are seeing in is this in millions of time. Okay, we get this kind of effect in millions of time in a display that you see today. So calculating the RGB value, okay, let's assume that calculating RGB value, R can be in a precise value, G can be in a precise value, and B can be in a precise value. So all of these pixel is doing one operation. Okay, all of these pixels need to be rendered out. So rendering out is calculating the RGB value. So each and every pixel in here is need to be doing one thing, calculating the RGB value, calculating the RGB value for a pixel. Okay, but the values that we are providing to calculate that RGB value is different. Okay, so GPU is really good executing one single instruction. We told that. Okay, the values that we are providing is changing. So you guys can see why GPU is a perfect match in here. The rendering in images, rendering or rendering our stuff in our screen. The whole screen at a given time is calculating RGB value, but the RGB values that we need to provide is different. Okay, single instruction, but multiple data. So that's why the GPU is created in order to accelerate graphics. Okay. The whole display, the whole application that you're seeing right now is rendered out. All of these processing power is taken to execute one action, that is to calculate the RGB value, but the RGB value that is needed to calculate that is different. So that's why only graphical rendering is powered by GPU at the start. Okay. So that's the reason we think we can assume that CPU can offload. Okay. So CPU don't have to think about calculating the RGB value for each of these pixels. Rather than it gives the opportunity, or it gives the task to something else, the GPU. Okay, so CPU is gonna transfer the calculating RGB values to the GPU, and GPU does it very fast. GPU is handling that part and it is rendering perfectly. So that's why GPU was invented. It can execute a single instruction but multiple data. Okay, hope that makes clear, because it's very important thing that you need to remember when you are using GPU for parallelization. Okay, otherwise you might get a wrong impression. GPU and CPU are the same thing, and it has some similarities, but no. CPU is different, GPU is different. GPU, as I mentioned, is capable of executing same instruction but with different data, like what we see in calculating pixels. But CPU on the other hand, it has a different purpose. CPU in the other hand, okay, it is completely different. It is not executing single instruction at a time. Okay, it is executing multiple instructions. Let's say, for example, playing a song and calculating, let's say, so calculating a Fibonacci numbers. Those are two different instructions. It's not the same thing. Okay, so whatever the instruction that you need to execute to achieve the task, the CPU is going to perform multiple instruction, and the data it's getting is multiple data sources. So the CPU is having MIMD architecture, while GPU is having single instruction, multiple data. Okay, so you guys can see why this is important at a given instruction set. Okay, CPU is doing multiple instruction, multiple data, as I mentioned, calculating maybe addition. Let's stick to basics, like addition, subtraction, multiplication, or something like that. So it might be different, but in a GPU, it's going to be always a single instruction at a given time. Okay, you don't expect that in a GPU, every time what we do is a single instruction. No, at a given execution cycle. Okay, not every GPU is baked in to do one single task. No, that's not what a single instruction means. At a given execution time, a single instruction is executed, but multiple data is provided. In a multiple data, multiple instruction is given. So CPU is handling this. So GPU and CPU are doing, both are doing parallelization, but in totally different ways. Okay, so remember this basic information, because this is very important when we are thinking about hardware what what kind of parallel algorithms, what kind of parallel hardware that we need to choose in order to do parallelization. Okay, that is also matters. So if you choose to go CPU multiplication, CPU based parallelization, your data should be multiple instruction and multiple data. Okay, but if you are trying to do GPU parallelization, it should be single instructed but with multiple data. So you see, hardware matters. Hardware matters when we are choosing a parallel algorithm. Okay, so let me give something that you guys can remember by the difference between CPU and GPU in like normal terms, like day-to-day activities that we are using. Okay. Somebody have to find a way to like increase the thickness of this thing. Okay, I have no clue why it's happening. Okay. So the GPU and the CPU in real world, if you take uh, by mean necessary, and remember this is only for exaggeration. I am not trying to harm or demotivate or devaluate any profession in the real world. Okay, I'm going to be taking some real world examples. So do not take this as an insult or any in a wrong way. I'm just simply mirroring the fact. Okay, so for example, let's assume a doctor. Okay, a uh, doctor can treat. It's not the best artwork. Okay, a doctor can treat multiple patients, right? Whether it is gonna be fever, okay, or a doctor can cater someone who is having back pain, okay, and doctor can have a patient with bleeding, surgery. Most of the doctors are in general practice. Uh, they have different um, capabilities, or they have different uh, what do you call different skill sets. Okay, a doctor can do multiple tasks. Okay, multiple tasks. It's able to perform. I'm not saying they can operate while they are treating a patient, but I'm simply mirroring saying if they were to multitask, okay, they can treat a fever patient. After that, they can treat what do you call, let's say, a back pain person. Then after that, they can treat a person with injury or something like that. They have multiple skill set, so they can perform different tasks. Let's assume a person who is working on a conveyor belt, or someone who is working in a packaging area. Okay, I'm simply saying, let's say a packager, a person who is doing packaging. Okay, that person is very good at packaging something. If some package comes in, he wraps around the sellotapes, he put it in a cardboard box, and he's excellently doing that, passing it to next one. The next item that he will or she will receive is the same thing, right? He or she will receive something like a parcel. They wrap it around cardboard. They have taped everything and move it along. The next thing is going to be the same. So the a packaging person is good at doing the same task in a rapid manner. Okay, the task is same, packaging, and when he or she is doing that, the same task is executed really quickly. There is no multitasking. If he or she is doing packaging, that's the only thing that they're going to be doing. But in a doctor's case, okay, if there is patients are coming, okay, unless it is like a fever day, like all the patients are coming one after another is a fever person, but in normal day, she or the doctor will receive a fever person, then then another person is having back pain. You get the idea. So they have different type of patients over there. Okay. So by the same logic, uh, packaging, the person who is doing packaging is doing that task only. But say, for example, that person is allocated for something else. Let's say now after packaging, he's move into something like, I don't know, uh, mm, transferring from point A to point B. Okay, there is a package. He or she need to move it from point A to point B. Okay, that's his task. Okay, so what will happen in this scenario? Let me zoom out. Okay, the task for the packager is change. It's moving A to B. Okay, but overall the instruction is same. Move A to B, move A to B. Same thing is doing. The instruction is changed from packaging to move. Okay, but he or she is doing only that at that time. If you take the doctor's scenario, doctor is doing the same thing. Okay, he will have only the order might change. A fever patient is now changed into something else. The doctor's scenario, it's a little bit different. Okay, so by guessing at uh, these two professions or these two real world scenarios, compare that to computer. Okay, computer task that we talked about. So which represent CPU? Yes, any guesses? A doctor represents a what? Yes, any guesses? Come on, guys. Yes, anyone? So this one is doing single instruction, but multiple data because the packaging are multiple data. She or he need to wrap sometimes teddy bear, another time maybe a lamp, another bottle. So SIMDC. The instruction is packaging, data might be different. So the person in here represents what? Yes, we have 100 people in the house. Come on, guys. Nobody. Everybody's sleeping. Hmm. My chat is working, right? Yeah. So the packager in here represent a GPU. Okay. So single instruction, multiple data. So in contrast, a doctor represent a CPU. Okay, multiple instructions. This is just a analogy that you need to remember. Don't write these in your papers. Okay. CPU is like a doctor. Okay. Uh, GPU is like a package man or something like that. Don't do that thing. I'm just emphasizing the thing to remember these things by using real world examples. Okay. So if you try to uh, come up with the come up with these things, uh, a GPU, what the packager has done cannot be done by the doctor most of the time because they are not used to doing such thing. Okay, the GPU has all the same thing. The GPU is not capable of switching the instruction and executing those things again and again. The GPU is designed in a way you need to have single instruction and multiple data. It's very efficient on that manner. But in CPU, it's the other way around. CPU is doing good in context switching. That means many instructions were given and instructions are changing. Okay. So things like graphic rendering are very good in GPUs and CPUs are not good that not that much good. Okay. But remember those two things have different purposes in our machine. Okay. So do not get confused on that one as well. Okay. So why I'm going along with GPU and CPU to emphasize the hardware matter in terms of selecting parallel computing. Okay. So remember, we do not learn that SMIMD, all those things for just for nothing. It's a thing that we need to consider when we are choosing a parallel algorithm. Parallel algorithms, even within itself, we need to select the correct hardware on that. Okay, remember that. So we talked about data size, data type, then the hardware. So next thing that we need to talk about when we are thinking about GPUs and all those things, the software side. Okay, so not only hardware matters, there is software considerations that we need to be considered as well. Software. Really, this one is much more huge. I don't know why it is drawing in smaller letters. Yeah, whatever. So we talk about hardware. Next thing is we need to think about is the software. So software wise, we need to think the parallelization. So especially when we are talking about software, we need to think in terms of um, parallelism enable softwares. Some programming language, we are talking in here, creating parallel algorithms. Okay, we need to think about creating parallel algorithms. So some software in terms of like programming languages, okay, especially programming languages, they do not have parallelism inbuilt. Okay, so software based parallelism sometimes is available, sometimes it's not. So for example, if you know programming languages such as Java, they have built-in software parallelization. Okay, if you know Java threads, okay, Java threads are made with software parallelization in hand. So they are using underlying hardware to communicate and do the physical threads, but there are software threads as well. Okay, so you guys might have heard the thread pool. So it is really a software-based parallelization. Okay, some programming languages do not have such capabilities. Like we can do software-based parallelization and managing those things with the CPU and all. So we need to make sure our software is capable of executing uh, thread level or software level multitasking or application parallelization. Okay, that is something that we must know. So for example, if you take programming language like JavaScript, which is similar in name at least. Sorry. So JavaScript does not have uh, threads or anything that related to. Yeah. Sorry about that. So JavaScript does not have um, the things when it is come to software threads or anything in between. So you need to remember not only hardware, software matters when you are selecting a parallelization in here. Okay. But there are other programs. If you have heard the term like CUDA, anyone knows CUDA? At least heard about it. CUDA. Yes. Do you know CUDA is where is coming from? It likes the origin of it. Yes, anyone? Where CUDA is originated? Who is like the owner of CUDA or who is dominating at least CUDA? Yeah, CUDA is from NVIDIA. Currently, the largest GPU maker and the most um, valued company. I think $3 trillion or something like that. Okay, so CUDA is introduced in order to do GPU parallelization much more faster. Okay, that means much more easier, not the faster way. Um, so NVIDIA builds GPUs, okay, and they are driving the world crazy right now with the revolution of AI and everything. So in order to program their GPUs, we rather than we are using GPU for only graphical processing, if anything that comes in like any parallel programming that we can do, we can utilize the GPU for that. Okay, nowadays uh, GPUs are not used in graphics at all. If you look at the market, most of the time GPUs are used in things like artificial intelligence, AI, okay, and things like what do you call that, blockchains, okay, and we have something like supercomputers. So those are like GPU's main usages right now. Earlier days, it was using for accelerating graphics. Now see where GPUs are at. Okay, so they applied in a um, different area of interest. Now they are in a different business. Okay, so why these these businesses or these subject areas need GPUs is because the heavily parallel algorithms that it can run. Okay, GPU is highly capable of running one single instruction but multiple data. So these applications, AI, blockchains, supercomputers that need to be doing parallel task, they will be utilizing GPUs. Okay, so in order to create these applications, okay, we need to program the GPU to in a different purpose. Okay, it need to be programmed to execute instruction. It need to be executed and return back the data. That kind of all those things should be done. And to make it easy, NVIDIA has introduced CUDA. Okay, compute unified data architecture or something like that. If I'm not butchering, let me double check. CUDA stand for Compute Unified Device Architecture. Okay, sorry if I get it wrong in the first time. So CUDA act as a programming, not a language, I say. It is a framework that we can use to uh, capabilities of GPUs, to harvest GPUs. As I mentioned earlier, GPU was invented for graphic acceleration. Now it's barely using in other than gaming industry and all those things. For expanding the capabilities of the GPU, not sticking into graphic generation and all, to expand those things, we need a smoother interface. Okay, so we can harvest the GPU power by using CUDA. We don't need to understand how thread works, how these things are work. We just need to program here and there, and we can utilize the GPU power with using CUDA. Okay, we will write some CUDA codes and we will try to understand what CUDA is all about, how CUDA is doing parallelization and so on and so forth. We will work on these things with GPU parallelization. Okay, so don't worry, we will learn CUDA in our course as well. Okay, so it's gonna help you to build your next AI adventure. Who knows? Okay, so basically, so we have the software factor as well. So CUDA comes in a place where uh, we have the control over what kind of things that we can control in here. Okay, so the CUDA uh, is something that we can use to um, create software-wise parallelization. Okay, so we talked about few things. Data size, that matters, the first thing. Okay, data size. Then what we talked about is, that is amount of data at least. Then we talked about data type. Okay, then we talked about hardware. Then we talked about software. So all of these components are going to be having an impact on our parallel and how we're going to make things parallel. Okay. Yeah. Mm, mm. So any questions with the dependencies of parallelization, hardware, software, and data and data size? So those are like the four pillars when we are talking about parallelization that we need to think about. Okay. All right. Next thing what we will do is we will do some parallelization using Java. Okay. So if you anyone here have used Java or practiced Java? Raise your hand, please. Nobody have used Java so far? Okay, that's good. So I see a couple of hands. I suppose you guys should be following a course or some sort of module. Okay, that's good. So for next slide for doing practicals on parallelization on Java. I need you guys to do these practicals if it is possible alongside me. Okay, I will demonstrate few of the concepts on parallelization, how Java can help, and what are the pitfalls that we can go. Like we talked about the four pillars, like the data, and all those things. And we'll see in action how those things can affect our performance in and everything. Okay, so in order to continue with this next lectures and everything, I need you guys to install Java in your machine. uh, Probably the latest would do. Okay, nothing old like 1.5 or something like that. At least install Java. I think last time I checked it was like 17, but latest version would just do fine. I think it's Java 21 is also available. I'm not sure. I did not follow that much, but uh, latest version would do. Just install latest JDK version, not Java version also. Remember to install JDK, okay? Not JVM, okay? Not the JVM, but the JDK, okay? So make sure to install JDK. Otherwise, what will happen is you won't be able to compile and all those things. Hopefully, you guys know these things. You don't. Make sure you know the syntax and semantics if you're not familiar with Java. So I'm not gonna teach you guys Java, but I'm gonna teach you how to parallelize using Java. Okay, parallel computing, how you're gonna do it, not how you're gonna not gonna teach you Java in this. Okay. Okay, since it is getting late and I'm a little bit tired, we will wrap up for today. Do you guys have any questions regarding what we have talked today? And make sure you guys refresh on what you have done. I think I have shared the link. Make sure to keep it safe until we make some sort of communication mechanism. So you guys can go and check out what we did on the parallel computing last time. Okay, let me stop recording.